Welcome back, everybody. So our last theorem, which we won't prove today, actually we can spend the whole next 2 weeks proving it, is the completeness theorem, Gödel's famous completeness theorem. The completeness theorem says that if a formula or a sentence phi is implied logically from gamma, then it can be proved from gamma. All right? So what this is saying is, if it's true that in every model of gamma satisfies phi, then there is an actual proof, a syntactical proof of phi from gamma, which is the most you can hope for, right? Because we know already from soundness that if you prove something, then that has to be true in terms of models. So now we're proving the reverse, that if it's true in terms of models, then you can prove it. So that means everything that is possible to prove, you can prove just with this modus ponens rule and the logical axioms. So in that sense is that this is the completeness theorem. It's telling you that the rules to write informal proofs, namely modus ponens and the logical axioms, are complete. There is nothing else that you need to do for your proofs. So whenever you do a proof, that's like if you want to prove something, if that something is true in this sense, then there is a proof with from there using those logical axioms and the rules. So it's going to be hard to prove this one, but let's talk about it a little bit more. So the second part is an equivalence statement. So they both mean the same thing, that if a set of formulas is consistent, then it is satisfiable. We already show from soundness that if you're satisfiable, you must be consistent. So this is kind of the reversal of that. And the proof is essentially the same as we had before. The proof of this is that if gamma is not satisfiable, then for every formula beta, gamma semantically implies beta. The reason for that is that if you're not satisfiable, you don't have any model. So it's trivially true that every model of gamma is a model of beta. Every model of gamma is a model of beta just because there are no models of gamma. So this is true for every formula. It will be implied, and also then that means that you will get also the negation that will also be implied. But then by the completeness theorem, by part 1, you will get that gamma proves beta and gamma proves not beta. So that's how you get that 1 implies 2, which we haven't provided. What's the reason that 2 implies 1? And this is by a contrapositive. If gamma does not prove phi, then by the reduction to absurdum that we proved last week, if you don't prove something, then gamma and the negation are consistent. Okay, so we're going to use this one in the opposite direction. If you don't prove, then this is not inconsistent. So if you don't prove phi, then gamma together with not phi is consistent. But then by part 2, gamma together with not phi is satisfiable. But then that implies that gamma does not logically imply phi, because gamma logically implies phi means that every model of gamma is a model of phi, and this being satisfiable says that there exists a model of gamma which is not a model of phi. So that means gamma cannot imply phi, and that's what we get from this contrapositive. Cool, so those two are equivalent, and together they are called completeness theorem. We're actually going to prove this one. We're going to show that if you're consistent, then you're satisfiable, and that's going to imply the other one. Okay, and then this is actually going to get this together with soundness. We get if and only if. Essentially, we get that logical implication is equivalent to syntactical implication, and we get that consistency is equivalent to satisfiability using soundness for the other direction. Okay, so one corollary of this that is we've been like using for a long time is compactness. So the compactness theorem follows directly from here. The compactness theorem has two versions. I also like this one too, which we saw already that they are equivalent. The first one says that if gamma logically implies phi, then there's a finite subset of gamma that already logically implies phi. And equivalently, we say that this is the same thing as saying that if every finite subset of a gamma is satisfiable, then the whole gamma is satisfiable, right? So we use both versions. Both are equivalent. We even prove that they are equivalent. So that's compactness. And why does it follow from completeness? Well, it's very simple because by completeness and soundness together, we know that logical implication is the same as a formal syntactic implication, right? And so they're back and forth, they are the same. So if a whole set of sentences proves this sentence phi, that means we have a deduction, a formal deduction of phi from gamma. In the formal deduction, we can only use finitely many sentences, right? A formal deduction is a finite list of formulas, and some of those come from the assumptions, but only finitely many. So we are using finitely many of the assumptions in the proof, not more than that. So we can take a finite subset, which are the ones that are used in the proof, and that's enough to prove phi, which again, if you prove phi, then by soundness, you logically imply phi. So that's the proof of compactness. So compactness is very easy if you look at formal deductions, and completeness and soundness tell you the formal deductions are the same as logical deductions. Okay, so we'll actually do this proof in the next coming weeks. See you guys later.